Do I even have my... Where's my pen? There we go. I was convinced that... Now I should probably open the fucking... I apologize. I did not anticipate that you would be coming back, so I closed all the things. Come on.
When everything is closed, does your computer run okay?
It's like fast enough to use Overleaf, which is like basically the main use case for my computer. It's all I do. Well, I should probably plug in the tablet. If you could see me IRL, you would see me attempting to touch my pen to a tablet that is not plugged in. Alright, good. Now, why is this not drawing? What a crazy day. Alright, there we go. So, for fuck's sake. Why are you not drawing?
I believe in you, tablet.
You can do it. Did you not just see it draw a moment ago? See, it does that.
I don't know, did I?
See, this is an illusion. Alright, maybe if I unplug and replug the tablet. There we go. Alright. So I think the last thing I was attempting to render the things that you had just said. So if there were... let's see if I can remember this now. We wanted to make P minus XA or something. And we wanted to fix the distance between these guys to be some L, which would mean Q by necessity has to be at some point L minus X, and then I don't know what to call the height, minus B or something. Maybe this guy's at B, this guy's at A. So anyway, so we were just trying to label the different possible paths, and I was trying to take your suggestion that I think maybe I should use a different color, but I think you said that we wanted to kind of label these paths by this point at the origin, right? So clearly different paths are going to hit this interface at different origins, so I'm trying to label these different origins where it hits the interface by this variable x, right? So x is now going to be the distance between P and the origin. Good, okay. So suppose we've done that. Now my question to you is, what is the function that we are trying to optimize here? So what is the thing we want to maximize or minimize so we can convert this to a nice calculus problem?
I believe that we want to minimize... Okay. Another thing, I'm thinking that our origin, O, in this case, is... I assume we are given V1.
Yeah, V1 and V2 are known, so you can treat them as constants.
I believe that the slope of PO is about V1, if I'm not mistaken.
The slope. So that would be true if this were a position versus time graph, right? Because velocity is the change in position over change in time. This is a two-dimensional trajectory, right? So this slope of P has nothing to do with V1, right? This guy's traveling, this is like x and y, right? So the slope is not related to v1, but I think what you're getting at is that the time it takes for the light to travel from P to O, the time it takes is certainly related to v, right? Because v is, well, let's see, if v1 is, the distance over time, so just by algebra, the time it takes to move from P to O is going to be v1 over the distance. Right. So with the point labeling that we've done on the pink axes over here, what is the distance between point P and the origin O? This hypotenuse.
Pythagoras is going to be x squared, well, anything. The square root of x squared plus a squared?
So the distance is root x squared plus a squared, which means the time it takes, just by, 8th grade, speed is distance over time, the time it takes the light to move from P to O, which I'll call T1. So T1 is going to be that distance you just told me, which is root x squared plus a squared, divided by the speed of that light in the medium, which is v1. Good. Okay, but there's a second piece, because now the light also has to travel from the origin O to the point Q, whose coordinates we also know. So how much time t2 does it take the light to move from O to Q in the same way?
So similarly, this can be represented by the square root of e minus x squared plus b squared.
B minus x, or L minus x, you mean?
That's an L.
So that's a cursive L, sorry. There's a
Okay.
b is the y and L minus x. Good. So you mean b squared plus L minus x squared.
Right.
All over v2, I think you said. Okay. Alright, that looks good. So now I'm running out of space for doing algebra, but I don't know what to erase. It's a very helpful diagram, but I think I have to erase this, so we can do some optimization now. So the total travel time for the light is the combination of these two. So I'll write this as capital T, which is the sum of this t1 and t2. So that should be root x squared plus a squared over v1 plus root b squared plus L minus x squared. I'm just copying the two things down there and adding them over v2. Okay, good. So the recipe that we wrote down said to keep eliminating variables until your function that you're trying to optimize only depends on one quantity now, and constants. So now we've done that, because this depends on only x, and constants like a, l, and the velocities, v1 and v2. So now we can honestly say this t is really t as a function of x, one variable. T is t of x. So now we want to minimize that, right? We want to find the minimum time over all possible values of x. So I think we know how to do that. I mean, up to the possibility that the derivative is not defined somewhere or some weird stuff at the endpoints, we know we want to take the derivative now, right? T prime of x. So I will ask you, because this is a huge mess and I don't trust myself to actually do the algebra, so you will do it for me. What is the derivative of this thing with respect to the variable x?
All right, we're going to break this into two derivatives before we go any further. That's just a mental note. I don't think you need to make any note of that.
Okay, that's good. So what's the first one?
Okay, so this is going to be some interesting chain ruling. Okay, well, not quite chain ruling. Regardless, we are going to apply the quotient rule, I believe it is.
Well, this is a constant, right?
And
so we don't need the quotient rule necessarily, right?
we don't? Well,
No, you could just say, derivative of, I don't know, some function f of x over a constant. You just pull out the constant. You say that's 1 over c times the derivative of the function itself. Right, so we don't need the quotient rule. Just take the derivative of the numerator and multiply the whole thing by 1 over v1, right?
so we're going to take the derivative of the top. We see by the chain rule that this is going to be equal to 0.5 times x squared plus a squared to the power of negative 1/2.
Good. And then the inside.
Right. And the inside's derivative is going to be, assuming a is a constant, this is going to just be 2x.
Good. Okay. Looks right.
Magic.
All right. So second piece, same spiel. Basically, the v2 is a constant, so we could pull that out and then differentiate this guy.
All right. We see by the chain rule that this is going to be 0.5 times b squared plus L minus x squared. Oh, wait. Yeah. You're adding on the stuff that I didn't say. Woo. Anything. And it's all, to the power of 0.5. Negative 0.5.
Get minus a half. And
Oh my
then
god.
I wrote that poorly, but okay. And then the inside piece.
And the derivative of that is going to be negative 2. Did I get cut out?
Yeah, sorry, I didn't hear it. What was it?
Negative 2x.
Negative 2, wait a sec. So, uh, L minus x squared. Let's see, I think we would have to
Right.
chain rule that, right? So it would be twice L minus x times a minus 1 or something?
Let me think. Okay, so we see that the b squared is eliminated. Well, not eliminated. It is 0. And we're going to need to chain rule the L minus x squared. Oh boy, more chain rule, I think.
Yes, you chain rule this,
Yeah.
and the outside guy is thing squared, so the derivative of that is twice thing, so 2 times L minus x. So 2 L minus x, and then the derivative of the inside, which is minus 1, right? Because there's a minus x. So I can put a
Oh,
minus 1
right.
inside.
Yeah,
Good, okay.
that makes more sense.
So I think you mostly got it, so let's just rewrite that in a slightly nicer way. So we see that these 2's everywhere cancel. We got 2's and 1/2's everywhere, so that's very nice. The first term then, I think, should be x over, there's a v1 downstairs, and a square root of x squared plus a squared downstairs, which is good. Second piece, as you say, ooh, minus, right? Because it's a minus L minus x. And then there's a v2 and a square root of this junk. B squared plus L minus x quantity squared all downstairs. So now I'm just simplifying what you told me a moment ago. Okay. So this is pretty good, but at the end of the day, we want to find an equation which relates these angles, theta 1 and theta 2. So the last step is to look at this expression and see, can we find a way of re-expressing these weird square roots, like the, I don't know, L minus x over the square root of b squared plus L minus x quantity squared? Can we re-express that whole thing in terms of, one of these angles, right? So to argue that we can do that, maybe I should redraw in what these points are. So we said Q was supposed to be L minus x with a minus b, right? So then that means that this triangle has the property that the height, this thing on the y-axis, this is a length b, and this thing on the x-axis here, this is L minus x. So I will ask you, what is the sine of this angle theta 2 in terms of those constants?
It's going to be L minus x over b.
L minus x, let's see, it's opposite over hypotenuse, right?
Right.
Yeah, so
I
not,
think. And we calculated the length of OQ to be a certain thing. Let me see.
well, you can kind of see by Pythagoras right away. The hypotenuse has to be square root of b squared plus L minus x quantity squared, right?
Okay.
Just Pythagoras that whole thing. So b squared plus L minus x quantity squared. Okay, so that's kind of nice because that is exactly what just appeared here, right? This, except for the v2, this thing with an L minus x upstairs and a square root of b squared plus L minus x quantity squared downstairs, that thing is exactly what appeared in our t prime of x. And as you've just told me, that thing is sine of theta 2, right? So that's pretty good. What about theta 1? So now I'm running out of space, but okay, let me erase some things. So I don't know which pieces to erase at this point, but using that simplification, we have found that the second term at least is minus, what did we just say, sine of theta 2 over the v2 that comes along for the ride. So let's see if we can play the same game with this first piece. So if the point P, as we've said, is supposed to be at minus xa, which means this length is x and this length is a, what is now the sine of theta 1?
Sine of theta 1 is equal to x over x squared, excuse me, the square root of x squared plus a squared. And that's identical as well.
Good. So that's, again, this whole thing except for the v1, right? So this whole thing is sine theta 1 over v1. Excellent. Okay. Now for the punchline, I will ask you, what is the equation which relates theta 1, theta 2, v1, and v2 with the property that that relationship guarantees a minimum of the travel time? Or in other words, it guarantees that the derivative t prime of x equals 0. So what happens, in other words, if I set this whole thing equal to 0 and solve for, I don't know, one of the angles? What do I get?
Say the question again.
So if I set this whole expression for the derivative, right, because we're trying to find the minimum, and the minimum, assuming there's no weird business at the endpoints, the minimum occurs where the derivative is 0. So I'm saying set this whole expression equal to 0 and solve for one of the angles, whichever one you like, theta 1 or theta 2, I don't care. So if I set this difference equal to 0 and solve for one of the angles, what do I get? Or solve for a sine of one of the angles, even.
I guess we can solve for this sine of one of the angles by, I think, we're going to have sine of theta 1 equals sine of theta 2 over v2, all multiplied by v1.
Yeah, so sine of theta 2, and then you say v1 over v2, for instance. So you're saying move this to the other side and multiply by v1. Okay, good. So
How did that come about?
I just
Because
rewrote what you told me. What did you say?
I added sine of theta. I think I added sine of theta squared over v squared. Why do I keep saying squared?
2.
Theta 2 over v2 to each side, and then multiplied each side by v1.
Yes, that's the same thing I did. If you add this term to both sides, then you get sine theta 1 over v1 equals sine theta 2 over v2. And then you say multiply both sides by v1. So on the left side, the denominator cancels, and I'm left with sine theta 1. On the right side, I'm left with sine theta 2 over v2 all times v1. And then I just said, okay, well, I'm going to write that like this. I move the v1 over v2 to the right, and write the sine theta 2 on the left. So that's the same thing, right? Because, of course, AB over C is, of course, the same as A times B over C, just by algebra, right? You can always, you can write the fraction any way you want.
Right. I forgot about that. Oh, I didn't see that.
Good. Okay. Well, so that's the equation you just told me a moment ago, which is a very nice, kind of compact and simple expression for what seemed like a pretty messy geometric problem, right? We had a lot of these square roots of a's, b's, and c's and things like that. But at the end of the day, we see that all of those constants, like the a and the l and the b, they all dropped out. The answer does not depend on them at all. And now we found that the answer relates these two angles, theta 1 and theta 2, only to the velocities, v1 and v2. Sometimes this is written in terms of the so-called indices of refraction, these n1 and n2, which are just the ratios. So n1 is just the ratio v1 to the speed of light in vacuum. So sometimes people prefer to write it in this way instead. That's fine. But the punchline is that the answer only depends on the speed of the light in those two media, and the answer tells you what the relationship between the angles is going to be. So I just want to write that. Well, I'll show you the next slide that writes it a little more nicely, but in LaTeX, I mean. So the same thing you just told me a moment ago, write the total travel time as a sum of these two, Pythagorean distances divided by the speeds. Set the results, the derivative of the result, I should say, equal to 0, and solve. Do some trigonometry to replace those by angles. And then you find this very nice result, which you could write by, say, dividing by, v2 in the way that you wrote it a moment ago. So you find this very nice result where this is indeed the relationship between the angles and the velocities that light actually takes when it travels between media. So we should be careful, because all we've done is set the derivative equal to 0, and we know that this could either be a max or a min. So we should be careful and check that that's actually a minimum. But by the first derivative test that we had a few slides ago on that summary, we can see by looking at this that if you are to the left of the critical point, which means x is smaller than this value, where this thing equals 0. If x is smaller than this thing, then the second term is going to be larger, because this thing has a minus x. So when x is smaller, this thing gets larger, because if you subtract a smaller quantity, then you get bigger. So this thing is going to be negative to the left of the critical point. But on the other hand, to the right of the critical point, if x is larger, well, this is a larger quantity minus something which subtracts a larger quantity. So if you subtract a larger quantity, you get more negative, and if you take a positive number and subtract something more negative, then you are more positive. So this is again the argument I made a while back, that if you look at a point where the derivative is 0 and say, okay, to the left the derivative is going to be negative because you're decreasing, and to the right the derivative is positive because you're increasing, then that tells you it's actually a minimum. So that's good. I'm just being systematic and checking that we've actually found a minimum instead of a maximum by accident. But okay, good. So if you're convinced of that, then we have successfully derived Snell's law. So this is, for instance, why when you're in a swimming pool and you look at, I don't know, some tall object like one of those pool noodles or a human standing in the pool, you may have noticed if you look in the pool, it seems like there's this kind of slant that you look at the person and it seems like there's a jump, right? There's some distance, you look at the person under the water and then look at them in the air, and it seems like there's some distance between them. I don't know, there's some distortion where it seems like the location of the object jumps as it moves from the water to the air. That's precisely because of this relationship. There's an angle because the light travels along two different linear paths in the air and the water. So I think that's very cool. Okay, thoughts on this?
Christian tries to explain diffraction.
Well, wait, this isn't diffraction, right? Yeah, we're not talking about diffraction, we're talking about...
Trying to remember the word. I don't know.
It's free propagation. There's no
Yeah.
there's no diffraction, but it is a distortion effect, right? Good.
Necessary. I don't know what was necessary.
You can tell based on how difficult that explanation was for me that I have not been in a pool in about 10 years. I think the last time I've been in a swimming pool was when I took the MIT required swimming test, where you have to swim 2 laps. Since then I've not
Wait,
been...
seriously?
Yeah, it's been a while.
I want to know some of the stories of kids that have gone to the swimming test and failed.
If you fail, you can just take a swimming class to remedy the deficiency, but thankfully I was able to pass. Okay, other thoughts on light and the Snell's law stuff?
I have no thoughts or questions.
Good, okay. We may not get through anywhere near all of these slides, but anyway, we'll try to get through Act 1 at least. Okay, next thing. So this is straight out of Spivak. I actually like this problem quite a lot. So we're designing a garden. This doesn't really look like much of a garden to me, but imagine it is, and we're planting flowers or something in this circular sector. So the garden is going to be in the shape of this circular sector with radius r, which is labeled, and some central angle theta. So this thing looks like Pac-Man, which subtends an angle theta. Now the punchline is that it has to have a fixed area A. So this is going to be one of the things we use to eliminate extra variables, right? There's a constant A, which is the area. So given that the area is fixed, what value of the radius r and this angle theta in radians should we choose so that the length of the fencing around the perimeter, so in other words this length in pink, the perimeter is minimized? What should we pick for r and theta that minimizes the perimeter P? Okay, so first thing I will ask you, what function should we write down, or what should we do first to convert this to a problem which is susceptible to our optimization toolkit?
I believe we can start by looking at the formula for the area of a circle, except with a certain bit cut out of it.
Yeah, good. Okay, so what's the area of this junk, this guy with an angle theta?
I believe that this can be represented theta over 2 pi radius squared.
Good, so theta over 2 pi times pi r squared, and the pi's cancel, I think, so this should be what, theta over 2 r squared, I think?
I believe so.
Good, so since the area is fixed, this thing's a constant, I'm going to go ahead and solve for, I don't know, one of these like r. So we're trying to eliminate anything which is constant. So if area is a constant, maybe I should solve this in terms of r, for instance. So if I do that, let's see, move 2 to the other side, so I have 2a over theta equals r squared, and then I take a square root, so that r will be the square root of 2a over theta, since a is constant. Okay, so that gives us r. Now it looks like we're trying to minimize this thing, the perimeter. So the perimeter has two contributions. It has one from these kind of edge pieces that are both equal to the radius, and then the perimeter has a second contribution from the outside piece, which is this junk, right? So what function should I write down for the perimeter now?
We've seen that perimeter can be represented by theta over 2 pi. Let me think. Theta over 2 pi 2 pi radius? Trying to remember stuff.
Yeah, you're trying to remember the circumference of a circle? Yes, so 2 pi r is the whole circumference, and then you say take the fraction of that corresponding to this fraction of the total circles. So that's good. That gives the outside junk, and I claim you should add something to that because of these two Pac-Man mouthpieces. So what should I add to that?
Plus 2r.
Yeah, 2r is good. Okay, so now this is where we reach the point in that recipe where I say it kind of sucks if your function depends on two variables, right? Because we're only learning single variable calculus, not multivariable calculus. So we want to eliminate one of those variables and write this as a function of one variable. But thankfully we've done that. As you told me a few moments ago, we've solved the radius in terms of a constant a and the variable theta. So on your behalf, I will go ahead and substitute this expression for r as a function of the constant a and the variable theta into the thing you just told me for the perimeter. So on the one hand, the 2 pi's cancel. This is what, theta r or something. So we have theta times r.
Can you check your connection?
Ah, good. Is the connection shitty? Ah, it has turned yellow, so that's probably... Oh no, now it's red. Fuck.
Oh no, it's
But now it's
that
green.
explains it.
Is it better now?
Slightly.
Claims to be green. I can wait. Oh, you just sent a very pixelated picture. I don't know.
Not just pixels on top of pixels. Oh no.
Oh, it's such a mess. Well, it claims to be green, so it should get better reasonably soon. Well, in the meantime, I will write out the substitution, and hopefully it will be readable by the time that the connection is restored. So, let's see, the 2 pi's cancel. Theta times r is this 2a over theta. plus twice r, but r is 2a over theta. And then I'll just do some square root stuff. So theta over square root of theta should be, let's see, theta under the square root plus, this should be 2 root 2a over theta. Okay, so I'm just doing algebra while the connection restores itself. So, okay, making more room at the top. Is it legible now? Can you see what I'm doing?
It actually just paused for quite a bit. Now I see what's going on.
Okay, good, good. So I just substituted into the formula you gave me for perimeter the formula we got before for radius. Okay, so now we're good. This is a function of one variable, right? You plug in one variable theta, a is a constant, and this gives you the perimeter. So I claim, again, now we know how to find the max or min of this single variable function, p as a function of theta, by taking the derivative. So this is where you'll come in. So if I have this sum of two terms downstairs, what is the derivative p prime of theta?
Wait, what did I miss?
So if we have this function p of theta, this thing, the sum of two terms, what's the derivative with respect to theta?
Alright, we're going to chain rule again. Yeah.
Nice.
So, first, by addition, we can take the derivative of the left element and see that by the chain rule that this is going to be equal to 0.5 times 2a theta to the power of 0.5, negative 0.5. And that is all times 2a.
Good. Okay, then the second piece.
And this is going to be, I think, once again by the chain rule, it is going to be 2a over theta to the power of negative 0.5. I don't know why I said that. Regardless.
2a, hold on, this, maybe I should rewrite this as
Right.
2, I'm pulling out the constant piece, right, because the theta's downstairs, so this is theta to the minus 1/2. So I think when you chain rule, the theta won't be to the minus 1/2, it'll be to the minus 3/2, right?
Wait, how did you get a? Let me think.
How did I get this thing?
The connection being bad is not helping.
I apologize. Yeah, I was just rewriting this because in the second term, we have, let's see, a 2 square root of 2a, but since theta is downstairs under the square root, that means that overall theta is raised to the minus 1/2 power, right? So I'm just writing it this way to emphasize that when we power rule the second term and subtract 1, the theta will end up being to the minus 3/2, not to the minus 1/2, right? So,
Okay, yeah, power to power is multiplication.
good. Okay, so with that in hand, what should the second piece be?
So I'm going to product rule, even if it's not necessary to make my life easier.
Well, I mean, this thing's a constant, so we don't even need the product rule.
Yeah.
Just take 2 root 2a times the derivative of the second piece, the theta to the minus 1/2.
Right. Oh, right, it would be 0 because of the product rule. Yeah, yep. Wait, why does it product rule? I didn't mean product rule. I'm very confused if you can tell. It's going to be times negative 1/2 theta to the power of negative 3/2.
Good. Okay, so this is, let's see, halves cancel here, halves cancel here, so I think at the end of the day this should be, let's see, a over, a over square root of 2a theta, and then this thing, 2's went away, so that's minus root 2a times theta to the minus 3/2, but that's, let's see, 1 over square root of theta cubed, if you like. That's theta to the minus 3/2. So this thing equals 0 is the idea. So I'll just erase this to make some more room, but if we solve this for the place where p prime of theta, the derivative equals 0, what angle theta will I get? Or what first step should I do to find that angle theta?
I've been asking you to do it a lot, but could you restate the question?
Sure, yeah, so if we're trying to solve this bottom equation, so I'll just rewrite it. Maybe I'll rewrite it with some algebra. So this will be square root of a over 2 theta, that's the first term. I'm just moving this a upstairs into the square root, minus square root of 2a over theta cubed equals 0. So I claim we're trying to solve for the critical points, the place where this derivative is 0. So I'm just putting a 0 on the right side. And my question to you was, what algebraic manipulation should we apply to this equation if we're trying to solve for theta?
I believe that we can move the negative root of 2a times 1 over root of theta. Is that theta cubed? I can't tell.
Yeah, I think it should be theta cubed because we had a theta to the minus 3/2, right?
Yeah. So we're going to move that part to the right side, and I have an idea of what we can do.
Okay, so I move that over here, and now what?
What occurred to the 2a theta in the left term?
The 2a theta. Wait, you're asking what happened in the last step where I simplified the a over root 2a theta?
Right.
Yes, so I wrote that as, let's see, the a upstairs is the same as square root of a squared, so this is square root of a squared. And then I said, well, if that's square root of a squared, I might as well cancel 1a downstairs and 1a upstairs. Right, so that was the step I did to take this thing and write it as a over root 2 theta, right? So I just moved the a not under the square root into the square root.
Okay, because for whatever reason I was thinking of some saying that the square root of 2a theta equals square root of 2a times square root of theta and zeroing stuff out or whatever. I don't know what I was doing. Yeah, it wouldn't have worked now that I think of it, because I would have been dividing a denominator and not actually canceling anything out.
Yeah, I want you to be careful. I mean, these the a upstairs, I think moving it under the square root is better because it makes it clearer that these a's are going to drop out, right? So in this last step that we have here, we have square root of a's on both sides, and it seems like those drop out. So probably the right step next is just to solve for theta in terms of, well, I can rewrite this. This is square root of 1 over 2 theta equals square root of 2 over theta cubed, right? So I think we can solve for theta pretty quickly from this step, right?
Why does clarify why you have removed the a's?
Because a is positive, so we can divide both sides by square root of a, right? So if we divide the left side by square root of a, that cancels the square root of a in the numerator of the square root. And in the same way, if we divide by root a on the right side, it cancels the root a upstairs. So maybe it helps to write this. I mean, let me just rewrite this equation.
I understand it.
Okay, good. Okay, so if we've done that, then how do I solve for theta next?
Can we square each side?
Looks good to me. So 1 over 2 theta is 2 over theta cubed. Or if you prefer, 1 over 2 is 2 over theta squared. So I think we're almost done. Move the theta squareds to both sides. theta squared equals 2 times 2, which in most countries is 4. So I think we can solve pretty quickly and say, okay, that means since we want theta to be positive, theta should be 2 in radians. Theta's 2 radians.
I was almost confused because I thought that 2 times 2 equals 2.
I have made that mistake myself. I'm embarrassed to admit. But, I mean, thankfully today I'm somewhat more lucid, so I think 2 times 2 should be 4. Good. Okay, so that's the value of theta, 2 radians, that minimizes the perimeter. And we solved, I've already erased the equation, but we solved for r in terms of theta using this fact that the area is constant, right? You told me that area should be, let's see, pi r squared times the fraction that this subtends, theta over 2 pi, which means that thing is theta over 2 r squared. So if theta is 2 radians, then that means the area is just r squared, or r is the square root of a. So again, it's a very nice result. The way that this problem was stated in terms of the circular sector in this garden, you wouldn't have expected that the answer ends up being so clean that theta must be 2 radians to minimize the perimeter, and r must be exactly square root of a. I find that very surprising. That is uniquely picked out by this problem that seems to have very little information baked in. But yeah, apparently that's it. So, good. I apologize for the mess of algebra here, but thoughts or comments on this question?
I was expecting it to be theta equals 0.
Theta equals 0. Okay, so that would just be, there'd be no area. That would just be a very straight line, right? It would basically be an infinitely thin garden. Yeah, that would be weird.
But what if that's what you want?
Well, I don't know. If you have body image
You
issues,
can all own a garden that way.
I want an infinitely thin garden in my life. Good.
You already do.
Yeah, I mean, I have no garden, so that means I have an infinitely thin garden. But, surprisingly, I did not make any mistakes in the algebraics. That is the same answer that I found when I wrote this out, whenever the hell I wrote this out. Just to recap, indeed, we used the area for the circular sector, which you told me, solved to get rid of this r in terms of the constant a, wrote the perimeter, found the fixed points, and then found that, the stationary points, critical points, whatever, there's so many words for places where the derivative is 0, found places where the derivative is 0, and notice those occur at theta equals 2 and r is root a. So again, I've emphasized this a few times, that when you find places where the derivative is 0, you should check whether they're a max or a min, because sometimes you'll find the wrong one, which is not appropriate for the problem at hand. So how do we know that this is a minimum of the perimeter rather than a maximum? One way to check that is to say, well, I know the max and min occur either at a critical point or an endpoint, so I can compare this value that I just found at a critical point to the values at the endpoints. And, you know, as you said, you thought maybe it would occur at theta equals 0, or the other endpoint is theta equals 2 pi. Theta equals 0 actually doesn't work, because then the area is necessarily going to be 0. So that doesn't satisfy the constraint that the area is fixed. So that endpoint is ruled out. The other one, theta equals 2 pi, gives the perimeter, just by, you know, the ordinary pi r squared formula, this gives the perimeters 2 square root of pi a, which is bigger, right? Because 2 square root of pi a is bigger than square root of a, just because 2 root pi is bigger than 1. So we know that we've actually found a minimum, because that thing is bigger. Good. Okay.
How is 0 not fixed?
How is 0 not fixed? What do you mean by fixed?
You said that 0 does not qualify. Well, theta equals 0 does not qualify since the area is 0 and therefore does not fall under the definition of fixed.
Yeah, by fixed I mean in the problem statement we were told that we're handed some number a by fixed area, I mean like in the person who's handing you this problem says the area has to be some number which I tell you, right? The area has to be like 10 square meters. So it's fixed, you have to have that area. If you don't have that area, it's not a solution to the problem. So if the area is fixed and you say, all right, my solution is theta equals 0. Well, what does theta equals 0 mean? That means that there's no garden at all, right? That means that this thing subtends an angle. I'm drawing it very skinny to emphasize, but this is basically theta equals 0 is a garden which is really just a line segment. And a line segment, by definition, has area 0 because it has length but no width, right? A line segment has no area. So I'm claiming that this solution, quote-unquote solution theta equals 0, does not actually satisfy the constraints of the question. Because someone handed you the constraint, the area has to be 10 square meters, and you told that person, all right, make a line segment instead of a garden, and that person comes back and says, well, fuck you, the line segment has area 0, and I wanted area 10 meters, so that doesn't work. That's the point.
I'm imagining this happening in real life.
Imagining an argument with your garden contractor. Good. Does that answer the question, though? Why theta is equal 0 doesn't work?
Yes.
Okay. Maybe we have time to do the last part of Act 1, and then I can leave you to do your other stuff, because today went longer than expected. But, okay, I really like this problem. This is a classic calculus problem. So let me state it for you. We have these two hallways, and the widths can be different. So the width of this hallway on the left is some number a, and the width of this second hallway up here, at the top right, is some number b, which can be different. And I want to carry a ladder around this hallway. So I'm carrying a ladder of some distance. I'm carrying it up this hallway of length a, and then to get it around the hallway, I have to kind of rotate and carry the ladder around the corner to get it into the hallway with this length b. And the question is, what is the longest ladder? What is the greatest possible length of a ladder which can be carried around this corner? Because clearly if my ladder's too long, I'm going to hit a bottleneck where I can't actually get it around the corner. So we're going to try to maximize the length, or otherwise minimize the length of the bottleneck, to find what length of a ladder I could possibly carry around the corner. Good, so it's a very interesting problem. It's a very hard problem. And when I first looked at this problem the first time it was presented to me, I had no idea how to start. I didn't even know how to write down a function to maximize or minimize. So when you're stuck and don't know... Oh, what'd you say?
Is this going to be L equals the square root of 4a squared plus b squared?
L equals square root 4a squared plus b squared. This is not the result, but I'm curious, how did you guess this?
I forget.
So you just guessed a random expression and forgot how you guessed it.
I didn't guess it. Let me think. I think I was thinking about some rectangle with 2a times b area and solving for the diagonal there.
Ah, okay, so you're drawing some rectangle like this with an a and a b, but you had a 2a for some reason? So maybe it looked like this, like a 2a?
That doesn't work quite anymore.
Yeah, it's good thinking, but this is not quite what we want. So the problem is harder than that. So I will suggest first, since the problem is very hard, to look at an easier case. Right? So when we don't know how to solve a problem, we think, what is an easier problem we do know how to solve, and then start from there to get kind of a foothold on the real problem. So the easier problem I suggest that you consider is, what if a and b are the same? Right? So we now are carrying a hallway which has the same length before the corner and afterwards. So
Carrying a hallway.
Carrying a hallway. Man, I'm bad at talking today. Carrying a ladder around a hallway whose distance doesn't, or whose length doesn't change before and after the corner. It's a and a. So, kind of just by intuition, looking at this, what do you think is the longest possible ladder we could carry around this sort of symmetric hallway?
So we are not told about any of the lengths of the hallway. That is also not necessary info.
Oh, by lengths you mean this distance, like this thing.
Right. That wouldn't matter.
Yeah, that has no effect.
Well, crunch. I guess we can start by making a unit square of sorts at the corner. That might give us more information.
This thing. So this is a square with lengths a and a. Okay. So you say, let's look at this square with lengths a and a, because somehow when we're going around the corner, this thing is going to be relevant for the bottleneck. By bottleneck, I mean the point when you're going around the corner where the kind of length constraint is tightest, right? Where the smallest possible ladder could get through at the bottleneck. So I agree, identifying this square is useful, because it points out that kind of the bottleneck is sort of where you're, I don't know, diagonally like this, so that you're kind of intersecting the square that you just identified symmetrically right through one of its endpoints. Right, so there's where the bottleneck is. Let me put it in a different color. So this right here is the bottleneck. So using, as you've said, kind of Pythagoras and this unit square that says, okay, this distance is a here, and this distance here is also a. What is the longest ladder that could fit around the corner passing through this bottleneck?
Thinking. I believe that this is 2 root 2 of a.
Yeah, 2 root 2a. Good, because these are 45, 45, 90s, so each of these is a root 2a, and you say that there's 2 of them because the ladder has to go from each of from this corner to each of the 2 endpoints. Good.
Oh, is it root 2 times a or root 2a?
Oh, yes, sorry. Why did I write that?
I think I didn't make it clear enough.
Well, it's mostly because I didn't make any sense, because that would have the wrong units. Uh, right? Because a has a length, so square root of 2a wouldn't make any sense, because square root of meters is not a very good length, so good catch. Yes. 2 root 2 and square root times a. Good. This is the maximum length when a and b are equal.
And now you have me thinking, what is the square root of a first dimensional unit?
Yeah, the square root of a meter is a fractal dimension. So certain fractals have dimensions which are non-integer lengths, which is quite interesting, but would take us far afield from the current discussion.
Correct.
Okay, good. So we've solved the question in a simpler context when a and b are equal, and as a side effect, this has kind of signaled to us why this problem is hard. The problem is hard because a and b are not equal, so we don't know where the bottleneck is going to be. By bottleneck, I mean the point where the shortest possible ladder could get through. When a and b are equal, we know the bottleneck has to occur at this kind of 45, 45, 90 point, right? Just by symmetry. The whole problem is symmetric about reflection around this kind of bisector, right? This diagonal line here. So in this case, the problem is symmetric, and we can solve it much more simply. Just say, all right, it has to be this 45, 45, 90 thing with a 2 root 2a. When a and b are non-equal, it's much harder. So we're going to have to restate this as a calculus problem and actually solve by optimization. So let's do that next. We want to find the bottleneck now when a and b are different, right? So a is not equal to b. So the first thing I'll ask you is that if we're finding the length of the dashed line, which I realized was a shitty thing to say because there are at least 3 dashed lines on this figure, but I mean the dashed in bold, right? The entire length of the ladder. What is the length of this diagonal dashed line first in terms of x, y, a, and b, and then we'll eliminate y afterwards? But first, that length.
So the length of this is going to be a plus, excuse me, the square root of a plus x squared plus y plus b squared.
A plus...
I did.
Backwards.
Yeah, I did word that right. A plus x quantity squared plus y plus b quantity squared.
Well, let's see. So one of these... So let's look at the top right one. So this one, this hypotenuse is square root of x squared plus b squared, right?
Oh, I was doing the total distance.
Ah,
I
good.
don't know.
Well, oh, okay, sorry. I totally missed what you were saying. Okay, so you're saying let's do this thing and say b plus y quantity squared and x plus a. Oh, yeah, that works. That works. I just totally misunderstood. Good. So b plus y quantity squared plus this thing is a plus x quantity squared. Okay. That's fine. That's, hoo boy. Alright, so that's going to be b squared plus 2by plus y squared plus a squared plus 2ax plus x squared, if I can FOIL, right? Foiling out each of these. So that's good.
I was gonna say, why are you foiling out all of these?
Yeah, maybe I shouldn't. Maybe it's easier. I didn't solve it this way, so we'll see what's easier to do. Maybe I'll just leave it like this for now and see if we can simplify it better. Okay, so let's try to do that. Now, I claim we can eliminate y. So y is determined in terms of a, x, and b in the way that I've written this, and as a hint for why that's true, let me draw this thing. So this is b, a, y, and then I claim that these angles are the same. So we have some similar triangles here. So you can give me an equation relating ax, b, and y, which simply expresses that these I drew the wrong one. Damn it. This thing should go like this. There we go. Which expresses that these triangles are similar. What's the relationship we get?
Are you just asking for opposite angles, or?
I'm asking for an equation which involves the letters b, x, y, and a, which expresses that these two triangles are similar. Right? So similar triangles have ratios of sides which are equal, right?
Thinking. I heard a glass. Let's see.
If you're watching the video, you'll see me drinking Diet Pepsi, but that is, I don't know, not... That's something that our viewers on YouTube will be laughing at, seeing me periodically refilling my Diet Pepsi.
Lovely. Anyways, let's see. I think I already said that. Alright, we see that our theta can be represented as, let's see. Okay, it's going to be sine of theta equals, as I just hold my mic on, anyways, opposite over hypotenuse, right, is going to be y over the square root of a squared plus y squared?
Let's see, y over root a squared plus y squared. Okay, and then the other, the one from this triangle?
This is going to be equal to, let's see, opposite over hypotenuse. I keep forgetting this. This is going to be b over x, b over the square root of x squared plus b squared.
Good.
Yes. Struggling with algebra. It's not even algebra.
It's trigonometry. It's or geometry or something. I don't know. Good. Okay, so I agree this is true. Um, we could actually solve this and get a relationship between ax, y, and b by squaring both sides and doing some just manipulations. An easier way to do that rather than doing the algebra is that I'll just rewrite this in terms of not sine but tangent. Why tangent? Because tangent is opposite over adjacent. So if I do that, the opposite over adjacent in the first one you told me, well, opposite is y and adjacent is a, right? So this is y over a. And in the second triangle, opposite is b and adjacent is x. So I get this nicer looking equation. Y over a is b over x. So the nice thing is that we can eliminate y by multiplying both sides by a and see, well, that's very nice. Y is ab over x. You could get the same thing from the signs that you did. You just solve for y, but it requires a couple extra steps. So I'm not going to do that because I'm lazy. But, okay, so that's the elimination we need to do. Thoughts, or are you happy with that argument?
I have no thoughts or questions.
Okay, so now you will tell me what should I write for the length when we have eliminated y and written it just in terms of a, b, and x?
I need to stop playing with this knife.
Is this your Damascus knife that you have used to genocide a patch of hair on your leg?
No, it's just a random box cutter. It keeps getting me distracted, so I just threw it away. Let's see. Hmm. Oh, I see what you're doing here. So you just want me to insert AB over X into our prior equation.
Right, so let's get rid of y, basically.
Ah. Yeah. So this is B over... Why did I say B over? B plus AB over X squared plus A plus X squared. Wow.
A plus x squared. Okay, good. So this is the total length along the hypotenuse. I think this can be simplified a bit, because this is kind of a pain in the ass to take the derivative now. How should I do this? I think I want square root x. I'm trying to think of a way. Maybe we shouldn't. Okay. I'm trying to simplify it. Maybe we should just be a bit more pedestrian and say, okay, this is the length of the ladder. Now we're trying to find the bottleneck, so let's just take the derivative and see if we can find the value of x, say, at which this length is minimized, right? So that will be the shortest ladder we could carry around the bottleneck. So instead of trying to be clever, I'll just say, all right, what's the derivative now? dl dx of this guy.
So this is going to be 0.5 times everything there to the power of negative 0.5. I don't know why I say 0.5 if it messes with you so much.
You really like decimals for some reason. Okay, so that whole thing to the minus a half, and then that's a shitty minus a half. Good, times the derivative of the inside, right? So what's that?
So the derivative of the inside with respect to x. Oh boy. We see by chain ruling the first element that this is going to be 2 times b plus ab over x times... Let's see. Yeah, this is interesting.
Well, this is a times b times x to the power minus 1, right? So we can power roll that.
Right. Well, I'm confused. Oh, okay, yeah. So this is going to be negative AB x to the negative second power.
Right, so I'll just put that downstairs like that. Good, maybe I should put some big brackets around this bitch. So that's the first piece, and then you say differentiate the second piece by linearity, and what's that guy?
Differentiating the second piece is going to result in a... Oh boy. Okay, chain rule to see that it's going to be 2 times a plus x times x.
Or times
That's way
1,
too easy. Right, times 1.
Yeah.
Yep.
Good. Okay. So the reason I put all this junk on the first line with this, minus 1/2 power is at the end of the day we want to set this equal to 0, right? So if this whole thing's equal to 0, junk to the minus 1/2 is in the denominator. And the nice thing about denominators is you can multiply both sides by the denominator and they cancel. So that's very nice. Now all we have to do is set the piece in brackets equal to 0, right, to solve for the critical points where the derivative vanishes. This thing, well, let's see, the 2's go away, and I don't know why I just did that. If the 2's go away, I think we can move this to the other side, because this guy comes with a minus sign. So we're going to get something like a plus x equals, well, b plus ab over x. I move this to the other side so the minus sign is gone, times ab over x squared, right? I think that's right. So what should we do to solve this? We're trying to solve for x, right? We want to find the x where this thing is a critical point. So what should I do to solve this equation for x now?
I guess we'd start by factoring b out of everything on the right side.
Yeah, let's see. So there's a b here, here, and here. So you say, write this as, I don't know, b squared. I'm taking one b out here and one b out here. So that would be b squared times 1 plus a over x times a over x squared, if I did that right. Something like that.
Looks right. Hopefully it is right.
Hopefully. We'll find out on the next slide if this is right, because I'm freeballing here because I didn't solve it this way. Okay, good. Now what?
Should we just foil?
Foil this thing out. Yeah, I guess we could. So I'm gonna make some more room here.
How many times have we erased that?
Yeah, more than is probably appropriate at this point. Let's see. So you say, I'm actually curious if we could get this to work now. So on the right side, you say, let's foil this, which would be a over x squared plus a squared over x cubed, perhaps? Is that right? Because we distribute this guy, a over x squared over x cubed. It looks reasonable. Now I'm tempted when I see this to multiply both sides by x cubed to just clear the denominators. But if we do that, we get ax cubed plus x to the 4th, I think, equals b squared times x plus a squared. This looks hard to solve. Let's see. Do you see? Oh, wait a second. What if we factor out an x cubed here?
Oh boy.
X cubed times a plus x equals b squared times x plus a squared. We must have made a mistake somewhere, because we're adding two different quantities with different units. Right, on the left side in parentheses we're adding a plus x. A and x both have units of length. On the right side we're adding x, which has units of length, and a squared, which has units of length squared. And you can't add units with different length. So we must have made a mistake somewhere.
Probably the act of FOILing.
Probably. Let's see, this...
Well, would it be an algebraic mistake or a logical mistake?
I think it must be an algebraic mistake somewhere, because... Let's see, this is length, length... length... What? Oh, this can't be right. This is 1 over length... No, that's fine. This part's right. So I made a mistake when I told you we could x cubed, x, a squared, 1 over length, 1 over length. What happened here? A squared, wait, that doesn't make any sense. Ax. How did I do that? Multiply this by x cubed. A over x squared times x cubed is ax. There we go. Okay. This is looking better. Ax. That's good. So, that's good because now we can factor... What, an a out here? So we want... Yeah, this is looking better. Equals b squared a times x plus a. Yeah, that's looking better. Good.
Whoa.
So, x plus a's are gone. Alright, now I will ask you for the coup de grace. What is the value of x for which this this equation is satisfied?
X is the cubed root of b squared b squared a.
Cubed root of
I almost cubed.
I don't know if this is actually correct, but it's dimensionally correct. Okay, this looks reasonable. Let's see. I feel like we've made a mistake somewhere, because this doesn't look familiar, but let's see. Let's look at the solution I wrote yesterday and see if this actually matches. So we think it should be cubed root... Now, let me actually save this, because I'm curious if we got it right the other way. So I did it differently. Instead of writing the length of this whole diagonal with one Pythagoras thing, I broke it into two pieces and wrote the sum of these two lengths, and then had a second exercise where we were going to take the derivative and find the length of the bottleneck. And it looks like I found a different answer. Instead of, what was it, root b cubed, or sorry, cubed root of b squared a, I found this different result. B to the power 2/3 plus a to the power 2/3, all raised to the 3/2. So, wait, is that true? No, we got it right. I'm actually very excited about this. No, this is right. Good. So, holy shit, I can't believe that actually worked. I was just, wow. Okay, sorry, I'm very excited now. Yeah, that's actually right. So, because b to the power 2/3, a to the power 1/3 is the same by power to a power, that's b to the 2/3, a to the 1/3. Holy shit, I can't believe we did that. Okay. I was convinced I was going to make an algebra mistake somewhere trying to solve it a different way on the fly, but that's actually correct. Okay, so as you say, this x equals the cube root of b squared a is indeed the bottleneck, so the point where the shortest ladder could possibly get through. And then, since at the end of the day we wanted to find the longest ladder that could get across, right, the longest length of the ladder, x is not the answer that we want, because looking back at the picture, we really want the length of the ladder, not the length of x, right? So we found the correct answer for x, which is this thing, but to get the right answer for the length of the ladder, we still have to plug that answer for x back into the formula, which gives the entire length of the ladder and not just x. So that's the last step, which I won't attempt to do now. If you take the answer for x, which miraculously we found, and put it back into the formula, which gives the length of the ladder, then you get this whole thing for L. So this is the longest ladder you can carry around a corner, which joins hallways of length A and B, which I think is a really elegant formula. Look at this. I mean, you rarely see something this beautiful. You add two lengths raised to the power 2/3. You never see lengths to the power 2/3. But you add them raised to the power 2/3 and then raise their sum to the power 3/2, so that by power to a power you get something with units of meters. It's just a very elegant, nice result. And apparently we got it correct. So, good. I love this question. This is a classic, beautiful calculus question. But we should probably quit here because we have spent longer than I expected on just Act 1. But before doing that, thoughts or questions on the very nice ladder question?
So how do you do the same thing but with a couch?
How is a couch different from a ladder? Does the height of the couch matter? Or is it just the
No.
length? Okay. Well, if the height of the couch is negligible, then the same solution goes through. So we'd use the same.
Oh, I was thinking vertical height,
Oh, okay. So you need to know.
not depth.
This is like a D&D question now, because you're saying now if the vertical height matters for a couch, then you're saying that we have two hallways where the hallway becomes kind of shorter, right? You're saying we narrow from a hallway of height h to a hallway of height h prime or something. So this is kind of like a D&D question where you're going from, some tall corridor to a short corridor. But here I think the problem's a bit simpler because you would just say, okay, well, you just take the couch which has the shorter height h prime after the narrowing. So perhaps that's somewhat.
Oh, I was not thinking of vertical height. I was thinking of length times width being the important thing.
Length times. So you want the cross-sectional area of the couch to be what matters. Length times width.
And somehow being able to get that around a corner.
That's okay. That's very interesting. Okay, so now you say it's not the. Oh, I see. So you're saying let's think about carrying some, I don't know, rectangle or something around this corner, and now it's not the length, but it's this product, as you say, the cross-sectional area, length times width, which matters. I've never seen that problem posed or worked out, but that's actually very interesting. Now the area is important.
I wouldn't even say the area, just how this ladder is offset by a certain amount.
Ladder.
Is if you
By ladder offset, you mean the ladder has some, I don't know, width, or you're saying this is what I would have called the ladder before, and now you're saying the ladder is offset in the sense that there's really two ladders which are joined by some, diagonal displacement.
right.
Yeah, that's very interesting. I actually want to think about that and see if there's a way to write the problem in a way that uses this displaced ladder, but I've never actually seen that problem.
I'm surprised you didn't do this when moving in.
It's very, very important with, I once had to fill a U-Haul truck when I was driving home from Boston to Pennsylvania and moving out of my apartment, so I'm surprised I did not work out the optimum since I brought my couch home. What is the optimum, minimized storage space for putting a couch in a U-Haul? It's a good question.
Dude.
Okay, good. Well, we can do the other parts, the